Welcome to our project presentation. Our topic was IR-based distance calculation. I'm Parithi.
I'm Arhant. So the premise of our project was we were required to design and build a circuit that measures distance using infrared sensors. To do this, we tried four approaches and there were some challenges and we faced along those approaches. We'll discuss each of those approaches one by one. So let's start.
For the literature survey, we refer to this specific research paper by Tariq Mohammed, which discussed distance measurement using ultrasonic sensors as well as infrared sensors. And it compared the functioning of both of those in different environments, such as dark or light environments. It also discussed the uh, factors such as temperature, humidity, and accuracy, and the working of the circuit in those.
So the first approach was to use an Arduino to calculate the time difference. In this approach, the Arduino will send a signal to the transmitter, which will then send a IR pulse. And at the time, we'll start a timer along this. And when the receiver receives a pulse, we'll stop the timer and calculate the time difference. Using the time difference, we'll calculate the distance by the given formula. In this approach, the problem was it was a purely circuit working by the Arduino. There was not much hardware involved. There was only a transmitter and a receiver, and it greatly reduced the complexity of the project as all the calculations were done by the microcontroller, and there was no hardware calculation in the circuit. For the second approach, we thought of using a 555 timer IC. In this approach, what we would do is we'll start a 555 timer IC as soon as we send a IR transmitter pulse. We'll count the number of pulses till the time the IR receiver gets a signal. Then we'll multiply the number of pulses with the time duration of each pulse to get the total time. And then, as discussed above, we'll multiply it with the speed of light to get the distance. The problem we faced in this approach was the 555 timer's working frequency is 2 megahertz, which is too low for the domain we are working in, and it requires around 300,000 megahertz or 3 gigahertz, so which was not even possible by 555 timer IC. And the other issue we faced was this the clock frequency required a similar counter IC which can work at these frequency, which was not available or not entirely possible from our research. Finding a multiplier compatible with the circuit was very difficult since we needed to multiply some constant at each step of the circuit like speed of light, the time duration of each pulse, etc., which proved to be quite difficult.
The next approach was trying to replace the timer with a capacitor by measuring the charging time of the capacitor, but this was not easy because the capacitor charging could be inaccurate. Also, this would require us to manually measure the charging level of the capacitor, which would take away the automatic functionality of the circuit and reducing its complexity.
So our final approach was to use an R ladder based comparator array. In this approach, we'll similarly send the signal through the IR transmitter and receive it through the receiver. And once we receive the signal at the receiver, we'll amplify the voltage and pass that amplified voltage to a comparator array. The comparator array will give us a glow of LEDs based on the voltage levels, and using calculated voltage levels, we can find out the distance in which the object lies. So
This is the circuit diagram of the circuit that we ended up using for our final project. The components that we used are listed on the side, and the circuit is can be seen. So the leftmost part of the circuit is the Arduino, which is going to give us an accurate measurement of the distance, and which will be displayed on the OLED display. And right next to it is the receiver transmitter circuit, uh, which is the sensor part of the circuit. The receiver and transmitter will measure the voltage level based on the distance between them. This voltage will be amplified by the op amp, which will then be sent to the comparator array, which is on the rightmost side. This is the working of the circuit explained. So first, the IR receiver and transmitter send the transmitter will send an IR signal which is received by the receiver, and this voltage value will vary based on the distance between them. The push button, uh, once it's pushed, then at that instant the transmitter sends the IR signal. Then the output voltage at the receiver is amplified using the op amp, which is then going to the R ladder, and then based on the level of voltage, uh, a specific number of LEDs glow, which tells us the range of the distance. Along with that, the voltage that is received at the receiver is also read by the Arduino using analog read, and then this is used to display the exact voltage distance value on the OIE display.
So the working of the Arduino subcircuit was that we trained an ML model of for polynomial regression using the dataset we collected with the ruler. The equation we obtained was as given below. The y represents the distance in centimeter and x is the voltage level at the receiver. The R2 score of the model was 99.87%, so we have a pretty good accuracy with the model. So, and this is the curve we observed. So the working of the R ladder is that there will be a reference voltage at each negative terminal of the op amp, and at positive terminal will give the incoming voltage from the receiver. Based on the working of the op amp, there will be a case when the LEDs will glow, and based on the voltage difference between the positive and negative terminal of the op amp, and sometimes will they not glow based on the similar voltage levels. So when the LEDs are glowing, we'll get a approximate distance at which the object will be lying, and based on those ranges, we can calculate a rough distance of the object. So in the circuit, we have shown 10 levels, but in a final implementation, we only did 6 because of the voltage level we observed. Our voltage varied between around 1.5 to 5 volts. So we divided into around zero point 0.7 volt steps to get around 6 levels. So now our final circuit testing.
The final circuit was tested by using a ruler that we looked at for accurate distance values, and using by placing the transmitter and receiver at specific distances, we got voltage readings, using which we got the graph that was there. And uh, yeah.
So the main challenges faced were that there was not possible to build a circuit without using a microcontroller and having it automatic at the same time. If we were not able to find a timer IC which worked at 3 gigahertz of a frequency, and similarly a counter IC which worked at those ranges. It was difficult to make a R ladder because of the number of op amps we used, and there were issues with each of the op amp which we faced. There's a chance of inherent capacitance in the circuit messing up with the voltage levels. We observed this with the combined effect of stereo radiation when we were observing a significant voltage at the output receiver even when there was no transmission from the IR transmitter.
Here are some specific ways that we think the circuit can be improved. One of the challenges that we faced was the IR transmitter signal was not very strong. So if we could have a transmitter that has a higher output voltage, then this would help us in increasing the distance range that we can sense, also giving us better resolution. This will also help with avoiding stray IR radiation present in the surroundings. Also, we can use multiple transmitters and receivers at different angles to get measure distances without the IR transmitter and receiver being in a straight line, um, which is a requirement for our uh, circuit to work. Um, the We could also measure the distance between the receiver and transmitter, but also we can do it with an object, which was not possible here because we could only measure distance when the receiver and transmitter were placed head on. If we could get a better signal from the receiver and transmitter, then an object could also be measured by keeping the distance to an object could be measured by keeping it at a specific distance, and then that could be measured. And if the number of levels in the R ladder is increased, then we can have a better resolution in our circuit.
So this is the conclusion of our presentation. So finally, we trained an ML model with the 99.87% accuracy, which can accurately predict the distance at which the object is based on the incoming voltage values. The range of a circuit is from 2 centimeter to 50 centimeter with a resolution of 0.5 centimeter. We'll get an approximate range of the distance from the comparator array, and for the exact value, we can look at the OLED display, which displays the correct value using the ML model. Thank you.
Thank you.